Okay, so welcome back to another video. So in today's video we have the following question from the 2002 Putnam Exam, and this is question A1, and it is stated as the following. So let k be a fixed positive integer. The nth derivative of 1 divided by x to the power k minus 1 has the form p sub n of x divided by x to the power k minus 1 quantity to the power n plus 1, where p sub n is a polynomial, and we are asked to find what p sub n of 1 is equal to. And you can actually prove this using, you can actually show this using the Taylor series argument, but I'm not going to go with that. I'm just pretty much going to go with a more straightforward approach, and that's of course given with the nth derivative. So of course we're actually going to be taking the derivative and analyze how the behavior follows with the following p sub n of x in order to achieve to the fact that we can actually determine what p sub n of 1 is equal to. So this is actually going to involve a little bit of calculus, some analysis, but it also involves with just some bits of induction. I'm not really going to use induction exactly, which you can use to solve this problem as well, but I'm not really going to take to that certain approach, but it's a little bit in a sense that I will use it in some way. But other than that, let's actually just jump right in. So we have the nth derivative of the following function over here. So how about this? We'll call the following form of the derivative, we'll call this f sub n of x. So here, f sub n of x, and we'll say that that's equal to the following over here of the form p sub n of x. Then we divide this by, okay, so x, k, subtract 1, then quantity n plus 1. And how about for the sake of it, we'll actually solve for p sub n on its own. So p sub n of x is equal to f sub n of x, and then just multiply with x to the power k minus 1, then n plus 1. Okay, this will come in handy later. We'll come back to this eventually, but for now let's just get the tools necessary needed to move forward. So now let's actually notice something. So here we have the standard p sub n of x of, so the following form, of course, and that's the nth derivative. So let's actually take its successive term n plus 1. This is where I mentioned we're going to use a little bit of induction here, but not exactly proving using the induction. But we're going to start with the successive term of p sub n plus 1 of x. So what that says is if I were to plug n plus 1 to our little like recursion relation, the formula, in other words, we could say, is that p sub n plus 1 of x, divide this, so that'll be x of k subtract 1. So replace n for n plus 1, so it's n plus 1 plus 1, so n of plus 2. Then you start to notice that, in other words, that's actually taking the n plus 1 derivative of this function over here. So I can write this as d, then n plus 1, then dx, n plus 1 of, so this is our function given 1 to the x, k, subtract 1. But in other words, you can rewrite this and say that that's actually just taking the derivative of the following form over here, since it's the successive, or that's our well, this is successive over here. This is our predecessor index. So here that means we could actually just we're just basically taking the derivative of this form over here. So this is p sub n of x, then divide that with x of k minus 1, then to the power n plus 1. So this is actually very straightforward with the calculus. You just use the quotient rule. So by computing this, I'll just take things one step at a time. So what we get is we do perform using quotient rule. So we have, this is actually just x, k, subtract 1, then n plus 1. Take the derivative of the top, the numerator, so this is prime of x. Subtract this, so p sub n of x. Then take the derivative of this denominator. So that means we move. So this is treated as the exponent, and then we're taking a derivative in terms of x. So when we do this, we have n plus 1, then x to the power k minus 1, then subtract the exponent. So this is just n. And then take the derivative of the inside. This is basically because of chain rule right over here. So we take the derivative of the inside. So this is just k then x, then to the power k minus 1. And then this is all being divided by, so we have x k minus 1, then distribute the, n plus 1, then square. So if we rewrite this a little further, then what you can see is that you can actually factor out an x to the power k minus 1 to the power n, and then this is actually going to cancel out some terms. So what you see is that you can actually, I'm skipping the steps, but that's actually the step you take. But once after performing all of this, you're going to get that the following form for taking the derivative of this is defined as follows. So this will be x to the power k, then subtract 1, then multiply by p prime sub n of x, subtract with p sub n of x, and then multiply with n plus 1, then multiply with kx to the power k minus 1, and then that's just divided by x to the power k, then subtract 1, and then to the power n plus 2, like so. We notice that the denominator shares the same formula here, so what that has to imply is that the p sub n plus 1 of x has to equate to what's written over the numerator on the top. So therefore, we can write that p sub n plus 1 of x is the numerator, like so. So over here, I can just draw it like this. Oops, how about, so right over here, this is actually equal to p sub n plus 1 of x, like so. Alright, so we have that. So what I can do is now let's actually plug x equals 1 for the numerator on top, that our p sub n plus 1. So when we get this, so p sub n, so we have p sub n plus 1 of 1. Okay, so we plug 1 on the top. So let's see, if I plug 1 over here, then this is just 1 minus 1 to any power is always going to be 1, so 1 minus 1 is 0. This whole thing's just going to equal 0. I'll just write it like this for x equals 1. And then over here, so then this is subtract, so negative p sub n of 1. Then this is just be multiplied with n plus 1. Then plug 1 for x, so this is just 1 to any power. Like I said, it's just always going to be 1, and so it's just therefore just k. So we have p sub n plus 1 of 1 is equal to negative p sub n of 1 times n plus 1, then multiplied by k. How do we move forward from here? Well, we're gonna do a little trick. So we're actually gonna see our index for n plus 1. We're actually going to replace all the indexes it's associated with the right hand side, subtract its index by 1. We're going backwards, so we're actually going back to its predecessor index of the whatever is defined. So how about this? I'll write out some terms and I'll come back to you in just a sec. Okay, so here I wrote out some terms. So what I started off with, so what we're given was n plus 1 that we showed this equal to this relation here. So I subtract the indexes by 1. So we substitute n and then place back for whatever the n is associated with. So we have n plus 1 and n plus 1 here. Then if this was n plus 1, then you just subtract that. It's just supposed to be n. So subtract 1. You get the gist. That's how the relation works. You just plug in whatever the index is in association, going from n, then subtract 1 again, then subtract 1 again, because we're going backwards, so there has to be like a successive term that exists already, so we can just start backwards. But if we continue going backwards, then all the way up to, let's say, the ith term, then we found a general formula saying for negative p sub n minus I of 1 is equal, and then multiplied by n minus 1, then times k. What you'll notice is that if I were to plug this back, it actually forms a little iteration. So here's the picture you can see. So let's see if I do this. So if I plug p sub n of 1 back here, so we have negative and then negative p sub n minus 1, 1. I'm just gonna skip the work, but you'll see that in reduction it actually comes down to, let me write it this way. So if I plug p sub n 1 over here, then we just plug this back here, then we get the following. We have p sub n minus 1 of 1, then times n plus 1 of k square. Okay, now let's see if we go back to plug p of sub n minus 1 back into here, then we would have negative p sub n minus 2 of 1, then times n plus 1 times n, then times n minus 1. Forgot to put the n over here. Sorry about that. So there should be an n and then a k square. So yeah, n, then n, and then n minus 1, then k to the cube. Now if I do this again, then we plug in for p sub n minus 2 back over here. There's a negative, so that'll change to a positive. So p sub n minus 3 of 1. Then multiply with n plus 1 times n minus 1, then times n minus 2 to the times k to the 4th power. If you keep doing this, so on and so forth, then we just plug in our p sub n to the p sub n minus I of 1 back in. Then we actually can see we can actually forms a little generalization that is still equal to p sub n plus 1 of 1. So this entails that for p sub n plus 1 of 1, if we were to plug the iteration back for some ith term, then we have that p sub n plus 1 of 1 is actually equal to some the following. So we have -1, because you notice that these signs just keep alternating from positive to negative, and so on, right? So this will be I plus 1, and then we multiply by p sub n minus I of 1, then n plus 1 times n, then times n minus 1 times n minus 2, all the way so forth. So you see that that actually forms a little factorial all the way up to n minus I, and then add 1, then multiply with k to the power I plus 1. So now all you gotta do now is let's just actually plug n for I, since we want to show the following for n plus 1. So if I plug n back in, so that means how about I write it like this? Plug n equals I. Okay, good. So when we plug n equals I back in, so this will be -1 to the power n plus 1, then p sub n minus n of 1, then let's see, so n minus n, then plus 1, so this would just be 1, but you notice that this actually forms a factorial. So basically this is just what did we could say, n plus 1, then times n, then we just keep going so forth all the way up to 1, and then plug back in, or I'll say 1, and then put back k to the times k to the power n plus 1. Okay, and so rewrite this even further, then you could say that this is just the same thing, -1 n plus 1, then that's p to the 0 of 1 of n plus 1 factorial, and then multiply with k times k to the power n plus 1, like so. So we've shown that this extreme left hand side is equal to the right hand side with the relation. However, okay, but one more thing to calculate is that because we have p sub 0 of 1, and what is that? Basically, that says that if we plug 0 back for n, so f to the 0 of x, the 0 derivative basically is just the function itself, which is 1 over x to the k minus 1. So I put this back here. So f of the 0 derivative of k, so this is just 1 divided by x to the power k minus 1. Then plug 0 back here, so this is just that's just the exponent is just 1, so it's xk to the minus 1. If you just combine it together, the terms cancel each other out, and then p sub 0 of 1 is just equal to 1, like so. And now the last thing is that we're pretty much done, because we've shown that p sub n plus 1 follows the generalization of -1 to the n plus 1, then times 1, then times n plus 1 factorial times k to the n plus 1. So now we're being asked to find p sub n plus 1. Since this is just a successive term, we just plug n back to whatever terms originally fall into n plus 1, replace that with n instead. So therefore, we can say that p sub n of 1 is equal to, so this is just -1 to the power n, then times 1, then multiply with n factorial, and then multiply with k to the power n, like so. And there we have it, the final answer. The final answer drawn in the black box, like so. So yeah, nothing too complicated as so. So Again, you can actually argue this using Taylor's series or induction, but I went with more of a straightforward method using the calculus like so, and find the relation with the starting with the Pn plus 1 and then work our way backwards from there. So yeah, so that's pretty cool if you ask me.